NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, ladies and gentlemen. How's everyone tonight? Good. Well, thanks again for coming out to join us this evening. Where is the best place to find living life beyond Earth? It may be that the small ice-covered moons of Jupiter and Saturn harbor some of the most habitable real estate in our solar system. Life loves liquid water, and these moons have lots of it. Tonight's lecture will explain the science behind why we think we know these oceans exist and what we know about the conditions on these worlds, while focusing on Jupiter's moon Europa, which is a top priority for future NASA missions. And we'll also show how the exploration of Earth's ocean is helping to inform our understanding of worlds like Europa. Born and raised in Manchester, Vermont, tonight's guest earned 2 bachelor's degrees from Dartmouth College and his master's and PhD from Stanford University. He is now the Deputy Chief Scientist for Solar System Exploration right here at NASA's Jet Propulsion Laboratory. His research focuses on the origin, evolution, and distribution of life in the solar system, with an emphasis on moons of the outer solar system that likely have liquid water oceans. His work involves numerical modeling, laboratory experiments, and field campaigns exploring some of Earth's most extreme environments. His fieldwork has brought him to the dry valleys of Antarctica, the depths of the Earth's oceans, the icy permafrost of Alaska, and to the glaciers of Kilimanjaro. In 2011, he was selected as a National Geographic Emerging Explorer and has been featured in several television documentaries for National Geographic, Discovery, and PBS, and was featured in the IMAX film Aliens of the Deep. He has made 9 dives to the bottom of the ocean and was also a scientist on board James Cameron's 2012 dive to the bottom of the Mariana Trench. Ladies and gentlemen, please help me welcome tonight's guest, Dr. Kevin Hand.
Thank you, Mark. Thank you. Thank you very much. The question of whether or not life exists beyond Earth is one of the oldest, most primordial, unanswered questions that humanity still has. And that's much of what motivates my interest in these ocean worlds of the outer solar system. But just to be clear, tonight I will not be covering UFOs, alien abductions, furry little creatures from other planets with 3 eyes. When I talk about the search for life elsewhere, I'm focused on even the tiniest of little microbes, even that discovery, the tiniest speck on some distant world, would revolutionize our understanding of the science of biology and how our universe works. Now, this is a question that has fascinated me since I was a young boy. As Mark mentioned, I grew up in a small town in Vermont, and looking at this picture, I guess it's no surprise that I turned out to be a scientist. And I attribute my fascination with the stars largely to the clear night skies that Vermont provided. But books like this also helped to captivate my imagination, showing a rather optimistic vision for aliens in Jupiter's atmosphere, some sort of Martian creature with massive ears, and even some sort of dinosaur surviving somehow on the surface of a world like Europa. But I like to show this image for another reason, and that is that in that background you can see that these mountains of Vermont, our entire planet, is covered with life. And one of the beautiful challenges that we face in our search for life elsewhere is that our home planet, from north, south, east, west, high, low, hot, cold, our planet is teeming with life. And in fact, it's hard to find a spot on our home planet that does not harbor life. And the story of our search for life elsewhere is in part the story of this beautiful little planet reaching out into the solar system through our robotic spacecraft. Each of these lines here denotes a mission that has gone out to one of the worlds in our solar system. As we know here, we're just over 50 years into this endeavor of searching for life beyond Earth, searching for understanding the origins of our solar system, and someday, hopefully, going beyond our solar system. But our effort to find life elsewhere begins with understanding life on Earth, which brings us back to this tiny little valley nestled in the Green Mountains of Vermont. Finding signs of life on a distant world is complicated by the fact that life and biological processes have played such varied and significant roles on Earth, both in the past and in the present. How will we know if we found life on a distant world? What guidance can life on Earth provide for us in this search? Well, it would be easy enough if we landed on a planet and saw trees and grass and a tennis court. But so far that hasn't happened. And the situation quickly gets a lot more complicated when you consider simple forms and the signs that they leave on a planet. These mountains serve as a useful example. If you peel away all these trees and the grass and even the tennis court, you find these rocks. These are blocks of marble, mined from this old marble quarry. Some of this marble went on to be used in various monuments and buildings around the country and around the globe. And it has its roots in a story that began some 350 million years ago. If you rewind the clock of time, in this old mountain, we've got layers that represent an ancient seabed, layers in an ancient ocean that existed in the Appalachian region some 350 million years ago. Gradually, sand and sediments fell out of that ocean and formed the seabed. Some of the sediments were the tests, the skeletons of these simple creatures called foraminifera. The tests of foraminifera are calcite, calcium carbonate. And in this ancient ocean, these organisms lived and died, and their tests gradually sedimented onto the seafloor. And with time, that seafloor underwent changes in temperature and pressure, gradually transforming that evidence of life in the past into limestone and eventually into this rock that we know and love and call marble. Now, what's interesting about marble is that just looking at it, you don't see any sign of those complex organisms, the complex tests of the foraminifera. You have no direct evidence just by examining it that this tells a story of life in an ancient ocean. And yet, to the trained eye, through our study of life on Earth, through our understanding of biology and biological processes on our home planet, we've come to appreciate that, for the most part, when we find this stone called marble on Earth, it tells a story of past life on our home planet. So, what if we were to go to a planet like this, with a rover like this, and examine rocks like these? A landscape showing dotted with ancient stream beds. What if our Curiosity rover were to rove up and nestle up against a nice big block of marble? What would we conclude about that as a sign of past life on Mars? The answer is, frankly, we don't know. That's part of the challenge. Trying to figure out both the context and the formation and the history of a geological region on a world like Mars. And the adventure is just beginning. Who knows? We may someday find rocks like marble, or perhaps even more obvious signs of ancient life on Mars. But as much as I love the planet Mars and our search for life on Mars, for the most part, we are looking for life in the past. We are looking for evidence of life in the rock record on Mars. I want to find living life, life that is alive today, life that is living in an environment that is habitable today. Coupled with that, I want to explore worlds where we think life may have undergone a second independent origin from life on Earth. Probing this question of, is the origin of life easy or is it hard? And on Mars, there are some confusing components there. You see, early on in the history of the solar system, Mars and the Earth traded material back and forth. And in fact, it continues into the modern day. And so if we were to go to Mars and find a fossil, well, first of all, we would have a hard time discerning the biochemistry of a fossil. But even if we were to go to Mars and find living life and discover that it was based on DNA and RNA and proteins, we would then have a challenge of figuring out whether or not that life was related to the tree of life here on Earth, or whether or not it represented a second origin because of this transfer of material back and forth. And this comes to that issue of the tree of life here on Earth. Our tree of life has changed dramatically over the time period in which we've been exploring the solar system. Just some 50 to 60 years ago, if you mentioned the tree of life, this is the image that would come to mind. An image of Neanderthals not too far away in evolutionary timeline from dinosaurs and other large creatures. But we now know that the tree of life that we once conceived of is just the tiniest of branches on a tree of life that is dominated by microbial life forms. We are just that tiniest little twig in this beautiful tree of life with archaea, bacteria, and eukaryotes, most of which are single-celled microbial organisms. So might there be a second tree of life out there in our solar system? Could there be a forest of trees of life in our solar system and beyond? To probe that question, I think we need to explore these ocean worlds of the outer solar system. Shown here is a portrait of the ocean worlds of our solar system. At the center, of course, is the Earth. And around the Earth, I've placed Europa, Ganymede, and Callisto, 3 moons of Jupiter, Enceladus and Titan, 2 moons of Saturn, and even Neptune's curious moon Triton, we think, could possibly harbor an ocean. In that case, it would be liquid water mixed with ammonia and a few other things. But these moons of the outer solar system are covered in ice, and beneath their icy shells, we have good reason to believe that vast quantities of liquid water are there today and may have persisted for much of the history of the solar system. This information, this knowledge, is really transforming our understanding of what it takes for a world to be habitable. In the early days of planetary science and astronomy, the idea of a habitable zone was defined largely by the need to be at just the right distance from your parent star, such that you had enough energy to maintain a liquid water ocean on the surface in contact with an atmosphere, and that ocean could cycle with a seafloor and the atmosphere. And so we had this sort of Goldilocks scenario where if you were at the Earth-Sun distance, you could maintain a liquid water ocean on the surface. If you got too close, you got too hot, like Venus, and you could not sustain an ocean. If you got too far away, you got too cold, and you could not sustain an ocean. But what these ocean worlds of the outer solar system are telling us is that this is kind of an old Goldilocks. There's a new Goldilocks in town, and it's a Goldilocks that is not mediated by distance from your parent star and the energy that you get from your parent star. Instead, it's a Goldilocks zone for habitability that is mediated by tidal energy dissipation. And there's no better example for this kind of energy dynamic than Jupiter's moon Io, shown here. And what you're seeing on Io in that northern region is a volcanic eruption. Io is the most volcanically active body in our solar system, more volcanically active than the Earth. And it is so volcanically active because of the tidal tug and pull that it experiences as it orbits Jupiter in its slightly elliptical orbit. So the Jovian system, the large moons of Jupiter, provide us with this sort of new Goldilocks for habitability, where Io is kind of like Venus. Io has too much energy being dissipated. Io lost any water that it once had. The yellows, the reds, the whites that you see, those are all various forms of sulfur from the volcanic eruptions. At the farther reaches, you've got Callisto. And Callisto, though it has an ocean, though we think it has an ocean, Callisto's ocean is trapped beneath a very thick layer of ice. And that layer of ice is quite old, as evidenced by all the pockmarks on the surface ice of Callisto. All of those little pockmarks are craters. But in the middle, in this sort of new Goldilocks zone for habitability, we've got Europa and Ganymede. And Europa in particular, we think, might satisfy the conditions for habitability as we've come to know and love it for life on Earth. And that is needing liquid water, access to the building blocks of life, and some energy, some chemical disequilibrium that life can harness. And again, part of why these worlds are so compelling in our search for life elsewhere is that if we've learned anything from life on Earth, it's that where you find liquid water, you generally find life. From life in these extreme environments, from hydrothermal vents, hot springs in the Rift Valley, the coldest regions of Antarctica, where there's liquid water, even if it's transient, life somehow finds a way. From life in extreme environments to life of extreme lifestyles. Life on Earth all depends on liquid water. And this also helps to underscore this issue of searching for a different biochemistry, a different tree of life. For all of the crazy life forms, from the tiniest microbe to the craziest rock star, we are all not only connected by the DNA tree of life, but we're also connected by the same fundamental biochemistry of DNA, RNA, proteins, and even ATP. Is there a different way of getting the business of life done? Is there a different way to form and to function life? We just don't know. But when it comes to these oceans, how do we think we know they exist? Well, it all begins, of course, with our exploration. And here at JPL, we've been at the forefront of exploring these worlds. For Europa and Enceladus, the champions of that exploration are the Cassini spacecraft, shown at left, and the Galileo spacecraft, shown at upper right. And of course, these spacecraft would be useless if we couldn't actually get the signal back, and the Deep Space Network, shown at the bottom right, is essential in getting that signal back. And it's through these spacecraft that we've managed to reveal the beauty of worlds like Saturn. And I'll begin with a little bit of a description of why we think we know an ocean exists on Saturn's moon, Enceladus. Here's Enceladus with Saturn and Saturn's rings in the background. Enceladus is a curious moon. It's only about 500 kilometers in diameter, not too much bigger in span than sort of the Great Lakes region. But you notice something immediately when you take a closer look at Enceladus. The northern hemisphere is dotted with all these craters, whereas the southern hemisphere, there are essentially no craters, but you have these tiger stripe fractures. The surface is telling us a story. In the north, those craters have been around for a long time. In the south, the absence of craters tells us that this is a fresh surface. And these fractures, which we've now come to call the tiger stripes, if we take a closer look and get just the right angle, as the Cassini spacecraft has managed to enable, we get what I would argue is one of the most beautiful images ever collected in our solar system exploration. An image of plumes erupting out of fractures from the south polar terrain of Enceladus. Normally when I give this talk, audiences ooh and ah at the fractures. Clearly, this is the JPL audience has seen Enceladus all over. But of course, part of what's exciting is not only can you see the plumes, but you can see fresh snow or fresh deposits along some of these fractures. And zooming in, one of the highest resolution mosaics of Enceladus shows these fractures up close, where these boulders along some of the fractures are just a few meters in diameter. And part of what, of course, we want to accomplish with our future of exploration is developing and designing the robotic spacecraft that will dive into these fractures, down into these regions where we have good knowledge of plumes coming up, connecting to an ocean below. The sunlight here gives you some view into the deepest regions of some of these cracks. And in a few of these pockets are where those fractures or where those plumes are coming out. So on Enceladus, we've got this curious situation where the ocean is literally jumping out at us. The Cassini spacecraft has flown to within 25 kilometers of Enceladus' surface. It's sampled what we think is material derived from the ocean, determined that there are salts in that water, that there are organics in that water, that there are compounds like carbon dioxide and methane in that water, which could, of course, be quite useful from an astrobiological standpoint. Now at Europa, the situation is quite a bit different. Enceladus, we can see, is active today. Europa, the evidence for activity, the evidence for plumes on Europa is still under study and is a bit tenuous. But Europa is a much larger world. It's about 3,000 kilometers in diameter. And any plumes that we would expect to erupt on Europa would not go nearly as high as the plumes on Enceladus, which extend outward for some 500 kilometers. But nevertheless, we think that the fracturing that we're seeing in this surface ice is in part caused by the tidal energy dissipation in the past, perhaps in the present, creating these fractures and lineaments. This ocean is, of course, maintained through this tidal energy interaction. Europa is about the size of our own moon, but orbits Jupiter, which is some 318 times as massive as the Earth. And so the liquid water ocean on Europa is about 100 kilometers deep by our best estimates. And if you do the math, it turns out that Europa's ocean contains roughly 2 to 3 times the volume of all the liquid water in the oceans, seas, and lakes on Earth. Showing that pictorially, here's an image that some colleagues at Woods Hole put together showing all of the water on Earth rolled up into a blue ball. That blue marble is all of Earth's water. Now, the first thing that you should appreciate when you see this image is that, of course, we need to take care of our home planet and protect the scarce water that we have here. If you do the same calculation for Europa, you end up with a blue marble that contains about 2 to 3 times the volume of all the liquid water found here. Now, as I mentioned, on Europa, we don't have the smoking gun of plumes erupting. We haven't seen any new fractures forming. That, I would argue, is largely due to limitations in our data, limitations in what's been returned by the Voyager and Galileo spacecraft. But we have very good reason to believe that that ocean exists. And the discovery of this ocean, I like to break into 3 easy pieces. The first piece is to find a rainbow connection. Much of what I do here at JPL is spectroscopy. And spectroscopy is basically a scientist's fancy word for studying rainbows. If you take a rainbow and turn it on its side and look at the intensity of the different colors, the different wavelengths, that is essentially a spectrum. And by looking at the variations in intensity of the various colors, you can reveal important information about the composition of the water in the atmosphere, the other compounds in our atmosphere, the composition of our sun. And so spectroscopy is an incredibly useful tool for getting at surface and gaseous compositions. And that's exactly what astronomers did back in the late 1950s and 1960s. They turned telescopes to the Jovian system and measured the surface of Europa. And what they found is this: an infrared spectrum, an infrared rainbow turned on its side, creating this spectrum with a highly diagnostic stepwise function with absorptions at 1.5 and 2 microns that is indicative of water ice. And so by making that rainbow connection, by doing the spectroscopy of Europa, scientists were able to first discover that Europa's surface is at least covered with water in the solid phase. The second piece of the puzzle is to babysit a spacecraft. And the spacecraft being babysat was Galileo, and the babysitter is the Deep Space Network. By carefully monitoring the position of the Galileo spacecraft as it flew by Europa, the Deep Space Network and the scientists working on tracking the spacecraft were able to measure the slightest of deviations due to variations in Europa's gravity. And through that determination, which involves a lot of math that I won't go into tonight, though I imagine some members of this audience would love to dive into this, through careful analysis of the gravity perturbations that were experienced by the Galileo spacecraft as it flew by Europa, and doing the gravity inversion for the moment of inertia, that leads to an internal mass distribution or internal density distribution for Europa, where we've got an iron or an iron-sulfur core, a silicate or rocky mantle, and then an outer layer, a layer of roughly 100 to 200 kilometers of unit density material. And the simplest explanation for that unit density material is water in either liquid or solid phase. Now, the gravity information is insufficient to reveal the density difference between solid and liquid water. And so the second piece of the puzzle leaves us with this picture of Europa, where we've got a lot of water, but we don't yet have an ocean. To get to the ocean, we need the final piece of the puzzle, and that I like to make the analogy to adhering to airport security. And my apologies for this fuzzy picture. This is a picture that I took at John F. Kennedy Airport, and I was trying not to get arrested, so it's a little bit blurry. But so what happens when you walk through a metal detector at an airport? What's happening is that you're walking through a time-varying magnetic field. And if you've got a conductor in your pocket, that time-varying magnetic field in that little doorway gives rise to induced electric currents in that conductor in your pocket. And those induced electric currents give rise to an induced magnetic field. And within that little doorway are special detectors that are searching for that induced magnetic field, and the alarm goes off. Well, out at Europa, when the Galileo spacecraft flew by Europa, the alarm essentially went off. Galileo had a fancy compass on board, a magnetometer, and that magnetometer was able to detect an induced magnetic field around Europa, a magnetic field that was not intrinsic to Europa, but which was being caused and mediated by Jupiter's incredibly strong time-varying field. Again, a lot of math that I won't go into tonight, but what this third piece of the puzzle leads to is that you need some near-surface conducting layer, analogous to the conductor in your pocket when you're walking through airport security. You need some conductor in your pocket to create that induced magnetic field. And the best explanation for that induced magnetic field is a salty liquid water layer near the surface of Europa. An iron core, sure, that's conductive, but it's too far away from the spacecraft to explain the induced magnetic field signature. Those rocky silicates, they're not conductive enough to explain that induced magnetic field signature. Ice, even ice doped with salts, still not conductive enough. The best explanation for the induced magnetic field signature is this salty liquid water ocean overlain by an ice shell of a few to maybe 10 or 15 kilometers in thickness. And here is one of the highest resolution mosaics that we have of the surface of Europa. This is the airplane view if you were able to look out across Europa. These ice cliffs with dark material that we know very little about, jutting up from below, fractures that perhaps have formed recently, or perhaps they formed tens of millions of years ago. At this point in time, we just don't know. And we don't know if some of this dark material is coming up from the ocean below, if it tells us about the oceanic composition, if it tells us about life forms living in that ocean below. The Galileo spacecraft left us with just enough information to feel confident about the presence of this global liquid water ocean, but not enough information to know whether or not that ocean is in fact habitable. And that brings us back to Earth and trying to understand some of these parameters, some of the constraints that we can place on habitability for life as we know it. And life on Earth is our guide for what it takes for a world to be habitable. As I mentioned, you need the liquid water, you need the elements for life, and you need some form of energy. And so what I'd like to do next is give you 4 short stories about life in extreme environments on Earth. First, life in the cold, then life in the deep, and we'll work our way from the surface of the Earth down to the deepest depths of our ocean. The coldest place on Earth is no challenge for life as we know it. This is the dry valleys of Antarctica. We were working there back in 2005. This is a particular area called Battleship Promontory, named in part because the early Navy pilots who flew through there thought that that geological feature looked like a Navy battleship. We were there testing out instrumentation and studying life in the rocks. Of course, around the perimeter of Antarctica, there are penguins, there are seals, there are all sorts of other creatures. But in the interior of Antarctica, there's no life except these tiniest of microbes that live in the rocks and some microbes which we think might live in the subglacial lakes. So the reds, the oranges, the yellows that you see there, that patina is all caused by life living within the pore spaces of the rocks. This gives you a nice view of one of these valleys. Now this is a bit deceiving here. It looks like this slope goes out into that valley, but really if you were to walk to the edge there and look over, this is what you would see, this vast cliff. And so here again, those colors that you see, those are all evidence of life in the rocks, surviving. Keep in mind that Antarctica is dark for half of the year. It's incredibly cold, incredibly dry. And yet what life is doing is eking out a living in the tiniest of pore spaces between the sandstone grains. So it seeks refuge, it seeks shelter in those pore spaces and manages to use the available sunlight for part of the year and some of the water that melts on occasion during the summer to then metabolize and grow and reproduce and to do photosynthesis. And part of what we were doing is developing instrumentation to study these cryptoendolithic microbial communities that manage to thrive just beneath the surface, beneath that protected veneer of these sandstone rocks. So in the coldest place on Earth, life has no problem. But let's go to some place that is cold and dark and wet, and a place where that gets to be a little bit closer to the situation that we might find on Europa. To do this, we'll travel up to Alaska. Some of this work was recently featured in National Geographic, and it involves studying these some 10,000 permafrost lakes that are along the north slope of Alaska. These little dots here are lakes that are open during the summer and then freeze over in the October-November timeframe. And some fraction of these lakes have methane bubbling out of them. We know it's methane because the methane gets trapped in the ice, and we can actually crack open the ice and light some of that methane on fire. And sometimes it's a lot of methane. Now, tonight I don't have time to go into a lot of detail about the biological work that we're doing on studying the microbes that are utilizing some of the methane and the microbes that are producing some of the methane. I want to skip to some of the technological development that we're doing to then study and monitor these ecosystems throughout the season. We can only, as humans, we're fragile, and we can only be up there for part of the year. But of course, here at JPL, we build robots that go to much harsher environments than the North Slope of Alaska. Why can't we build something that we can just set free and deploy to study these lakes autonomously for months to years on end? And to that effect, some of JPL's engineers, John Lichty and Andy Klesch and Dan Beresford, I think, might be in the audience. Brilliant team of engineers. We're up there studying these lakes, and we're trying to figure out some of the chemistry of the ice-water interface and what microbes are utilizing the methane. And to do that, we wanted a vehicle, a submersible, that did not disturb the water too much and that could have a very long lifetime. And we sort of had this collective aha of, well, a traditional submersible is very energy intensive because it's moving in 3 dimensions. Whereas a rover is quite efficient because when you get to a place you like, you can just stop and do the science. Well, why not just take a rover and turn it upside down and pretend like we're crawling on the underside of the ice? And so that's exactly what our team designed. We call it the Buoyant Rover for Under Ice Exploration. And along with doing this interesting mobility innovation of roving, of having buoyancy stick us to the underside of the ice, this past field season, I also set forth the challenge to our team to allow us to do Europa-like operations. Now, of course, the first step in doing a spacecraft operation is you've got to survive launch. And in our scenario, surviving launch is analogous to being trailed behind a snow machine on the Alaskan permafrost for about 20 kilometers. This is vibration testing. Coupled with that, we wanted a very small system, something that we could fit on the back of a sled. Here we're doing initial deployment and checkout. Here's John. You can see that we're on a tether right now. And what we're eventually building up to, that I'll show you in a few moments, is pulling that tether and operating the vehicle untethered, underwater, under ice, via satellite link, such that we could leave it there and go back to our nice warm Quonset hut and operate it in shirt sleeves. Here's one of the lakes that's got a lot of methane bubbling out of it. Andy Klesch here is poking through the ice, trying to make sure it's safe to walk on, and we'll pan over to a few of the open regions that still have methane bubbling out of them. And as you see, as we pan further and further to the right, I'm actually standing on pretty thin ice. And I've actually taken a dip into this water, not intentionally. It's cold, but we come prepared, and we've got lots of backup gear. So you can see that the methane is actively bubbling out. It's not hot, it's just the kinetic activity of the methane that maintains the open water. And now we'll dive under the ice. And this time, the rover is operating untethered via the satellite link. And the bubbles that you see coming out, those are methane bubbles. And the bubbles that are trapped in the ice that's methane that's being encapsulated in the ice as the ice thickens throughout the season. And so we've just begun to make this a platform that can survive for long periods of time under the ice. This past field season, we left it out there for 2 periods of about 30 hours. And John and Andy and Dan were able to actually hand over control to some engineers here at JPL to operate it via satellite link while it was under the ice. This is what the rover sees. We'll take a dive into the lake. This is an Alaskan sunrise. The sun doesn't get much higher in the sky. We'll go over to the little hole here. And I think you can hear it. Dropping in. And there you can see the rover vision that allows us to examine the lake floor and the ice-water interface. And so when we get to a spot that we then want to do sampling and scientific analyses, we can leave the rover there without expending excess battery power, and that potentially means that we can leave it out there for a full winter season. And as I mentioned, we were able to operate it both from the Quonset hut and from JPL. Now, what I showed you, it looked like fun, it looked nice and everything. Just to emphasize, there are many days that are not fun up there. And in fact, on the second deployment of our rover, we went out there and a huge storm had rolled in. It had blown down one of our tents, and recovering the rover actually turned out to be a bit of a challenge because so much snow had filled in over the ice, but eventually we were able to get it out. And a National Geographic photographer, Mark Thiessen, was up there with us and captured these beautiful images with a camera on a stick showing the rover in action. So we've gone to someplace cold, we've gone to someplace cold and wet and dark. Next, I'd like to bring you to deep places in our ocean, places that are comparable in pressure to the pressures that life within an ocean of Europa might experience. And I was fortunate enough to be a part of an expedition out to both the Mid-Atlantic Ridge and the East Pacific Rise to explore hydrothermal vents. This was part of an IMAX project spearheaded by James Cameron and Disney. We were on the Russian research vessel, the Keldysh, which has two deep ocean submersibles that can each carry 3 people. And these can go to nearly 6 kilometers or more in depth. I got to make a number of dives, and in some cases, we had an additional acrylic sphere rover with us. We actually had 2 of these, and we made dives on some of these sites with 2, 3, and even 4 submersibles at a time. And part of what we were studying are these hydrothermal vent ecosystems on Earth that revolutionized our understanding of the habitability of our own planet. These were discovered back in the spring of 1977, not long after Viking had set down on the surface of Mars. No one really expected that these hydrothermal vent systems would be anything more than geological curiosities. But in fact, they turned out to be oases for life. They were not just regions where microbes were eking out a living. They were places where microbes utilizing chemosynthesis formed the foundation of a complex food chain consisting of shrimp and tube worms and mussels and crabs. And so here, all of the white material that you're seeing, those are microbes that are utilizing the chemistry of the hydrothermal vents to do this process of chemosynthesis, functioning with that chemosynthetic metabolic pathway as opposed to photosynthesis, which of course requires the sun. But a site like this requires active creation of new seafloor. We also went to a region known as Lost City, shown here. This is a region that is off-axis from the spreading centers. And what's unique and interesting about this particular type of hydrothermal vent is that it's not powered by heat transferred from the mantle. It's powered by an exothermic reaction called serpentinization, wherein ultramafic rock from the mantle, is exposed to ocean water and drives a chemical reaction that's exothermic, i.e. sort of similar to like taking a hand warmer and shaking it up. And that leads to this diffuse venting and precipitation of things like carbonate. And it's around these sites, though it doesn't look quite as biologically active. There are many microbial mats thriving here, and one of the most profound creatures that I've ever seen on our planet, this creature, a large ctenophore spanning about 1.5 meters to 2 meters. This creature was just swimming around that chimney that I just showed you. And an interesting little story here. I went down on this dive in one of those acrylic spheres and got down to the bottom of the ocean and started to collect some samples. And we were communicating with the other subs, and James Cameron was in the other acrylic sphere, and they had not caught up with us. So we radioed up to them and we said, "Well, what's keeping you guys? What's going on?" I shouldn't say radioed. We acoustically transponded to the other submersible, and it's a real choppy communication, so it's hard to make things out. But we get a communication back saying, "Oh yeah, we've run into a little bit of trouble. Don't worry, we'll be down there at the bottom of the ocean in 5 minutes." So we keep on sampling, and it's about that time that I discovered this creature, because I was picking up a sample and I turned the rover a little bit, and there was this astonishing space bagel, as we first called it. And so we called back up to Cameron and to Paul, the pilot that was with him. We said, "You guys gotta get down here. You won't believe what we're looking at." And they said, "Oh yeah, we're coming. That little problem, it's a leak." And of course, the last thing that you want to hear from your friends and colleagues that are in a submersible is that there's a leak in the sub. So we said, "Are you sure you don't want to surface?" And they said, No, we think the leak will stop." Now, there actually is some logic to that, because the way that these submersibles work, these particular submersibles work, is that you get in from below, and there's a cork-like plug in the bottom. And as you drop further down in the ocean, the pressure increases, and the force pushing on that plug creates a tighter and tighter seal. And so they said, "Yeah, we'll just keep on going down, and that'll improve the seal." And sure enough, they got down to the bottom, and the leak persisted, but they didn't die. And in fact, Cameron was able to recover this astonishing footage of this creature in action. Arguably one of the most bizarre and beautiful life forms that I've ever had the great chance to experience. But okay, so these hydrothermal vents, these are great, but to be honest, they're not that Europa-like. The depths that I've been showing you are 3 to 4 kilometers, Lost Cities at about 1 kilometer depth. The pressures in these regions is equivalent to maybe 10 to 20 kilometers or so, perhaps as much as 30 kilometers below the surface of Europa. And we think that the sea floor of Europa may well be 100 kilometers or so down. To get to pressures comparable to those depths, you need to go here, to the Mariana Trench, to the Challenger Deep region of our ocean, a region where our ocean gets down to 11 kilometers. And I was part of an expedition to go back out to the Challenger Deep. James Cameron made the dive back to this deepest depth, and we also had a few robotic landers that we dropped along with the human submersible. Unlike the previous expedition, I did not get to go down to the bottom of the Mariana Trench. So when people ask me what it looked like, I say this. Pretty much like any other spot on the ocean. And you may have seen lots of pictures and video of this expedition. An incredible engineering achievement. The human submersible is a vertical dropping torpedo. It goes in horizontally like this, and I'll show you in a few slides what it looked like as it was dropping through the ocean. As I mentioned, I didn't get to go on a trip in it. James Cameron was the only one that made the dive to the bottom of the ocean, and quite a spectacular feat. The integration and testing of this submersible took place in a time frame of months. Cameron had been planning it and had a small core team that made some of the key features over the course of roughly 5 or so years. But really, the integration and testing took place from roughly October to November of 2011, and the big dive was done near the end of March in 2012. I won't go into it tonight, but at some point we'll have that team here to talk about systems engineering in a very tight time frame, because it really was an astonishing accomplishment. So Cameron came back alive on the human exploration side. That was great. Everybody breathed a huge sigh of relief. But a little bit of an anecdote for you. Though everything went off without a hitch, the team had planned on doing the big dive towards the end of January. If not January, then certainly in February. And if not in February, then sometime in early March. But with weather and a few problems with other things, those dates slipped. And when we started out the expedition, there was one date that Cameron could not miss. And that was that he had to be in London walking the red carpet on, I think it was March 27th, for the re-release of Titanic 3D. And this was some contract that he had signed in blood that he would be there. And lo and behold, with some of the delays due to weather and other things, we found ourselves on Sunday night, March 25th, still not having made the big dive. And Jim had to be in London less than 48 hours from there. But thankfully, on Monday morning, the seas were calm, and we were able to deploy the sub. It took about less than 4 hours to get to the bottom. The torpedo just dropped straight down. He was then able to traverse along the Challenger Deep for a few hours and then come back up. But of course, by that time, it was late on Monday, and he still had to get to London. Now, this is where I started to appreciate the dividing line between life as a scientist and life as a bazillionaire Hollywood director, producer, etc., as if it hadn't been clear before. So we're all kind of like, how is Jim gonna make this trip? When we got back out to the Mariana Trench after doing some repairs, we noticed this ship on the horizon, which looked quite small at first, but as we got closer, we saw that in fact it was a massive yacht. And it turns out that this is Paul Allen's yacht. And apparently this is one of the fastest yachts on the planet. And so Cameron needed to get from point A to point B. And he called up Paul Allen and said, "Hey, Paul, I'm going to be making a dive to the deepest depths of our ocean. Want to come out, check it out, and then help me get to Guam, where I can catch a plane and head on from Guam to through Russia and on to London." And sure enough, he made it to the red carpet just in the nick of time. And Paramount or whoever it was happy. And he lived, the story had a happy ending. Now, again, just to be clear, so that's the yacht that Paul Allen had and the fancy Hollywood stuff. The science team, this was our boat. A lovely little vessel called the Barracuda. And so it was a fine place to call home for many weeks. Just to show you the human submersible on the bottom, there it is in its sort of vertical position. And what's taking the picture in this particular image are these robotic landers that were built down at Scripps spearheaded by Kevin Hardy, a wonderful engineer down there, and overseen by Doug Bartlett, the chief scientist of the expedition. And these are telephone booth size vehicles that just drop down through the ocean, and when they get down there, they deploy that arm that you see on the side in the middle picture. And that arm has got a water sampling device, and there are cameras on board, and sediment cores and various traps to try and attract creatures. And so we deployed these on the Challenger Deep, and one of the great advantages of these is that you can leave them down there for a long time. And what I'm showing you here is video footage from the deepest depths of our ocean, the Challenger Deep, a depth of greater than 11 kilometers. And this is what you're seeing in the foreground here is that robotic arm, the water sampling device. And there's a fish head in the net there. And after several hours of just observing this fish head trapped in the net, what we observed are all of these shrimp-like amphipods collecting around the trap, feeding on the bait that we had left there. And this is astonishing. Not only is the deepest depth of our ocean a place where you might have simple life forms, but it's a place where complex multicellular life forms like these exist and thrive. Taking a close-up look at these, this is what they look like. Not the prettiest of creatures. And somebody in the audience always wants to know, well, what did they taste like? And sure enough, one of the ship hands grabbed one of these and popped it into his mouth and ate it, and subsequently ran to the side of the boat and returned the creature to the ocean, to put it politely. But okay, so that video from the Challenger Deep, astonishing, these complex creatures thriving down there. But as I showed, we had a bait trap out there, and so those creatures were attracted by that food. What do they eat when there's no fish head around? What is driving that ecosystem? We were not really able to answer that question with the drop in the Challenger Deep, but when we made a drop of the robotic landers in an area just a little bit to the northeast of the Challenger Deep, in a region called the Sirena Deep, we saw quite a spectacular sight. In this video, what you'll see is the robotic arm drop. It'll hit the seafloor and dust up a big old cloud, and you can see right away in the background there is a geologist and scientist's dream, outcrop. And those of you that have been part of the Mars missions know, of course, that scientists go crazy for outcrop because it actually gives us some geological context for what's actually going on in the environment. And so when we got the footage back and were able to piece together the images, this is what we saw. In all of the other regions in the Mariana Trench, for the most part, all that had been seen are just these sediment beds. No actual indigenous rocks that we could then connect geochemistry to. And what astonished us even more is that when you zoom in on these rocks to the right there, this is what you see. Yeah. We're calling these the bearded rocks of the Sirena Deep because they look like sort of a fuzzy rock. And our current hypothesis, and the evidence supports this so far, is that these filaments coming off of these rocks are microbial mats that are metabolizing fluids that are slowly percolating up from the ocean floor below, and from those rocks, utilizing the effluent from this process of serpentinization that I mentioned before. And so we think that in the deepest region of our own ocean, this exothermic process of serpentinization is providing the chemical energy needed to help sustain a microbial ecosystem that is then sustaining those complex creatures, those amphipods that I showed you in the previous video, which is evidence of not just a simple ecosystem in one of the harshest environments on Earth, but quite a complex and involved ecosystem in the deepest depths of our ocean, in a region that is as close to Europa's seafloor as we can get on Earth. So how does this all add up for what we want to do on Europa? Well, I'll give you my dream of dreams. In the dream scenario, some decades from now, we will deploy some highly capable lander that brilliant engineers at NASA and JPL are able to design that can negotiate the surface of Europa, avoiding cliffs and boulders, finding a nice, soft and flat landing spot, deploying a melt probe with some sort of heat source on the front end to melt through the ice, going all the way through that ice, leaving behind a fiber optic or some other communication cable to send data back to the surface. It reaches the ocean, deploys that front end nose cone, and out pops this autonomous underwater vehicle. We're of course not going to be able to joystick this from Earth, so this thing would have to be quite autonomous. It gets down to the bottom of the seafloor, and at least in our IMAX Hollywood version, we then find not only hydrothermal vents, but happy creatures that are delighted to see us, and we have revolutionized the science of biology. So that is the dream of dreams. Of course, we have many steps to take to make that possible. And right now, of course, NASA and JPL are in the process of studying various types of missions that would get us back out to Europa. And we're optimistic that within the next decade or so, we will return to this incredibly compelling world that could harbor life. And so I'd like to close with one of my favorite images from the history of space exploration. It's an image carved by none other than Galileo Galilei. An image carved some 400 years ago. It's an image that Galileo carefully traced out night after night, showing, let's go back to that one. There we go. There we are. As you all know, Galileo turned his telescope to the night sky and carefully charted Jupiter, and he noticed these 4 tiny little specks of light around Jupiter. Now, of course, in the early days of his charting these little points of light, he initially thought that they were stars, and so he named them the stars of Medici. Galileo was, of course, funded by the Medici family, and he was no idiot, so he knew that to keep the money rolling, he should name something after his sponsor. But he soon realized that these stars were moving. And night after night, he charted them and determined that, in fact, those 4 little dots were not stars, they were moons. They were moons of Jupiter. And if Jupiter had moons, then it must be similar to the Earth, because, of course, Earth had been, up until that point, the only world that had a moon. And so if things were going around Jupiter, then that went against that Aristotelian view of the Earth being the center around which everything else revolved. So with his careful charting of not just Jupiter, but of course Venus and the moon, Galileo was able to put the final nail in the coffin of Aristotelian cosmology and open the doorway to the Copernican revolution. And in the decades that would follow Galileo, we would come to learn and appreciate that the laws of physics apply not just here on Earth, but also to these worlds and wonders beyond the Earth. And in the decades and centuries after that, with the advent of spectroscopy and new techniques for studying stars and planets, we would come to appreciate that the principles of chemistry apply not just here on Earth, but also on worlds and wonders beyond the Earth. And then with the advent of our robotic exploration of the solar system and our investigation of worlds like Mars and Mercury and Venus, we would come to appreciate that the principles of geology apply not just here on Earth, but also to these worlds and wonders beyond Earth. But when it comes to this bizarre little thing we call life, when it comes to the phenomenon of life, when it comes to the science of biology, we have yet to make that leap. We don't yet know whether or not biology works on worlds and wonders beyond Earth. We have every reason to believe that it should. Our study of life on Earth leads us to think that life is likely everywhere where the conditions are right. But we have yet to do that experiment. And part of what excites me about the time in which we live, part of what excites me about the next few decades, is that for the first time in the history of humanity, we have the tools and technology to answer this age-old question of whether or not we are, in fact, alone in the universe. And so I hope that some 400 years from now, our descendants will be able to look back at this time in much the same way that we can look back at the revolution that Galileo's work began. Our descendants, some 400 years from now, will be able to look back at this time in the history of human exploration and scientific discovery. Not just this time, this place, the JPL, a premier place in helping to achieve the exploration and the science that needs to be done to advance these kind of discoveries. I hope our descendants will be able to look back at this time and this place and say, it was then, it was there, it was through the perseverance and the exploration that the discoveries were made that brought the universe to life. Thank you very much. So we may have a little bit of time for questions, and I think there's a microphone there. So if you have a question to ask, please, if you would, go to the microphone.
My name is Abhi, and I'm a summer intern here at JPL. My question is that in a not completely unlikely event of future NASA missions to Europa being pushed further into future due to budget cuts, what level of merit do you see in a flyby mission to Europa which could just sniff the water plumes and maybe deduce the chemistry lying beneath the icy shell?
Yeah, so in my opinion, we don't yet have definitive evidence of plumes that we could then direct a spacecraft to. I think that plumes are likely there. But if we were just to do a quick and dirty mission that's very simple, it would be a little bit hard to know exactly where the best place is to capture material to do the analyses we need to get done.
Hello. In regard to the auroras of Europa, is it possible that they will discover microbial life in the plumes of Europa, like they have discovered it in Enceladus?
Well, so at Enceladus, we haven't yet found life in the plume water, but we have found some compelling organic chemistry. And that, of course, makes Enceladus an incredibly exciting target to go back to. And I want to explore all of these worlds. In my opinion, we should be getting spacecraft out there doing science all throughout the solar system. And so one of the, but the fundamental of your question, if there was microbial life in the ocean, would it be ejected out, and would we be able to catch it? At this point in time, we don't really know. We're doing some experiments to try and see whether or not, for instance, in Earth's ocean, if you took the microbial cell densities in Earth's ocean water and pretended that that was Europa's ocean water or Enceladus's ocean water, how much material would you have to collect before you captured one cell? We don't know the answer to that quite yet, but that's part of the work that we're doing to sort of fold into these missions.
Thank you.
Thank you.
Could you tell me anything about the work, or if there is any work being done to look deeper into the hydrothermal vents themselves? We look at them when they reach the open ocean. I don't know how much water content you have and what's being pumped out of them, but is there a possibility of life deeper within those systems, and is there a way to actually plumb them with instrumentation?
Yeah, that's a great question, and there is some very nice work being done at a number of different institutions, Woods Hole, University of Washington, Seattle, Scripps, USC, and there's a project called the Ocean Drilling Program that has as sort of a component of it looking in areas that have or had hydrothermal vents. But this sort of folds into a passion of mine, which is developing the robotic tools to do exactly what you're saying, so we can actually kind of dive even deeper into the channels of water that are being cycled up through our ocean floor.
Hi, my name's Andrew. I'm a summer intern. Great presentation. It was really interesting, and I just have one question. If, regardless of whether or not we drill down and find life or not, once we do drill down, we're going to likely contaminate what's in there. So what are some means that JPL and NASA are working with to prevent that from happening? Thank you.
Yeah, it's a great question. You're a bright intern. So the Europa project here at JPL and the Planetary Protection Officer at NASA headquarters work very closely on addressing these issues. And any mission that would go near Europa or onto the surface would undergo a lot of cleaning and sterilization to make sure that we don't bring any Earth microbes to that potentially habitable ocean. Because, of course, the last thing we want to do is find a false positive. We don't want to go all the way to Europa and find an Earth microbe. And more importantly, we don't want to destroy Europa for the Europans. If they've got something going on in that ocean, we should let them keep doing what they're doing.
Hi. I was wondering if you can calculate theoretically the thickness of the ice layer on Europa based on the tidal energy and the temperature it receives from the sun.
Yeah, that's another great question. There are dozens of papers published on the topic, and not much of a consensus has been reached, in part because different processes happen for slightly different thicknesses in terms of convection and conduction of heat out from the interior. And so some scientists think that Europa's ice shell is, say, 15 kilometers in thickness, and much of that 15 kilometers is ice that is slowly convecting to transport heat, and then it's overlain by a brittle lid. Other scientists think that it's actually quite a thin shell, maybe a few kilometers in thickness, and most of the heat is being dissipated via conduction. So it's a topic of much debate, and it's one of the key questions that any future mission would hopefully address.
Hello, thank you so much for your presentations, really wonderful. And by the way, I really enjoyed your Europa report.
Well, thank you.
Everybody should see it. I wanted to ask you about the interesting news that came out a few months ago from the University of Washington of a paper that talked about the ability to find certain molecules in distant planets, potentially exoplanets, that could be indicators of life. And correct me, is it dimer molecules or Dimmler molecules?
Dimers, yep.
And is that something that's relevant to Europa or Enceladus or any of these outer ocean worlds? And where are we getting in terms of our space telescopes, potentially with the James Webb, in terms of being able to detect those molecules on worlds that are even farther out that may indicate the presence of life or photosynthesis or something happening on one of ththose planets that might be interesting to explore further?
Yeah, here again, I wish we could be moving faster. There are ground-based telescopes, the 30-meter telescope out in Hawaii, of course, James Webb, and potentially some smaller space-based telescopes that will come online in the not-too-distant future that will help be able to do spectroscopy of these exoplanet atmospheres. I wish we could move faster on that because it's such a fascinating area for exploration. Now that said, when we do eventually find a world that has these spectroscopic biosignatures of things like oxygen and methane, carbon dioxide, ozone, et cetera, that's kind of where we're going to be left. Unless we train our radio telescopes or our optical telescopes and find some SETI signal of intelligent civilizations there. One of the limitations of exoplanets, or one of the defining attributes, is that they are far away. And so someday we will know that there's a habitable planet out there, but then it will take us a long time to get there if they're not beaming communications to us. And that in part is sort of what drew me to Europa over 17 years ago or so at this point, is that worlds like Europa and Enceladus are worlds where we can actually send a robotic spacecraft to look for living life and something that we can touch and feel and determine its fundamental biochemistry. So I look forward to future discoveries on exoplanets, and that will be moving along in parallel with our exploration of our own solar system.
I hope you get more funding to do it. You got to get those landers to Europa. Oh.
Well, thank you, and
Best of
we've
luck
got
with it.
lots of bright young minds that are excited about STEM education who want to be part of the space program.
Well, again, a wonderful talk. Thank you so much. And my question is, I know there's a lot of possibilities for the next mission to go to Europa, depending on what NASA's funding is, what Congress decides, and that sort of thing, which is a real game sometimes. But what's the most concrete mission that is at the forefront of heading out to Europa at this point? Where does that stand? And you know about maybe how long it might take to send that off?
Yeah, so a great resource is to go to europa.jpl.nasa.gov, and that's got all of the publicly available reports and documentation. And another great resource is, so within NASA, there are these assessment groups for various regions, and the Outer Planets Assessment Group, or OPAG, if you just Google OPAG, you'll find lots of archived mission studies. And one of the studies that you'll find there is on the Europa Clipper, which is a mission that's being studied and analyzed here at JPL and other centers. And that mission would, if funded, it would fly by Europa and be able to examine the surface in great detail, both with imagery and spectroscopy. It would potentially utilize ice-penetrating radar to probe into the ice and look for water pockets and the ice-water interface. And it would have many other instruments that would help us assess the habitability of Europa. So Google around and look for Europa Clipper, and you'll also find all sorts of other studies that NASA has done.
Thank you.
And we got a couple of questions from the web. Thank you. is the theory that Europa is getting geothermal activity from the tidal squeezing of Jupiter's gravitational pressures. Yeah, so the question's about that tidal tug and pull, and the reason why we think Europa has this liquid water ocean is because of that squeezing as Europa goes around in its slightly elliptical orbit. Just imagine Io, but now cover it in ice and dial back the volcanism a little bit. That's perhaps what Europa looks like. What would Europa's energy source be for life? Well, if Europa has an active seafloor, there could be hydrothermal vents. But then another aspect of the energy equation for habitability on Europa comes back to the surface, where some of the work I do and my colleagues do here at JPL is looking at the surface radiation chemistry. And we actually know that Europa's surface ice has molecular oxygen trapped in it. It's got sulfate, it's got carbon dioxide, it's got all of these compounds that life on Earth loves to eat. And so if some of that surface ice mixes into the ocean below, that could be a very valuable chemical energy resource for life within Europa. And I'll just take one more here. Is there any reasonable prospect that we might find complex life forms in the European Ocean like the ones we have in Earth's hydrothermal vents? Very interesting question. And from an energy standpoint, it could be so complex life on Earth, even at those hydrothermal vents, it depends on oxygen that is produced via photosynthesis. So those tube worms, those shrimp, those other creatures that you see, they are breathing oxygen that's dissolved in the ocean water, and that oxygen comes from photosynthesis on the surface of the Earth. On Europa, we're not going to have necessarily photosynthesis generating oxygen, but we do have this radiation chemistry that is bombarding Europa's surface, producing that molecular oxygen that I mentioned. And so if some of that molecular oxygen is mixed into the ocean, there could be enough oxygen to potentially power complex life as we know it. But from an evolutionary standpoint, this becomes a very intriguing question. What made complex life on Earth possible? Is it, from an evolutionary standpoint, contingent on some events, or is it a sort of convergent evolutionary process? Will complex life arise on any world that's got enough energy to help power it? We don't know. And so going to Europa, looking at some of that ocean chemistry, and potentially finding not just simple life forms, but more complex life forms, is something that I dream of doing. So I'll finish there, and thank you again so much for being a great audience.